All right, so we now know how the Henderson-Hasselbalch equations, both of them, are derived. On your equation sheet, you're only given this one, so be aware that there's also this other equation, but you're only given the pH form of it. Um, the note is important. The note says that if this ratio right here that you see between the conjugate base and the weak acid, or the conjugate acid and its weak base, if that ratio is written in moles, or you're given mole amounts, you can easily slip it into this ratio. Once again, because molarity is moles over liters and moles over liters. And if the liters are the same, your moles is the ratio that you're really seeing changing. Likewise over here, if this is molarity over molarity, so if the volume is the same, you can look at it also in the same ratio as the mole units. All right, to understand this relationship, you have to know what a log function is. So here's my simple log function, and I drew the graph of log of x here. Um, at 1, meaning x is 1, what happens is this is where the y values start to turn positive here. Below 1, you're seeing negative y values. So please be aware when I say y values, it's really log of x values that are negatives. So if a minus right here is greater than that of HA, that means this ratio is going to be greater than 1, which means you're going to have a positive log value here. If it's a positive log value, your pH is going to be greater than the pKa of that value. Okay? The pH is greater than the pKa. So this is the scenario. Now, if HA is greater than that of A minus, so you're seeing this scenario play out, your function, your ratio is going to be less than. Log of x is going to be a negative value. And with that negative value, you're going to subtract. Your pH is going to be less than that of your pKa because you're going to be subtracting this negative value, or adding the negative value to the pKa. When this is equal, what is log of 1 equal to? Well, log of 1 is 0. And so this pH equals pKa. These ratios, it works also the same way with the pOH. When we speak of buffering and how buffering occurs, you will not see a pH changing that much. And usually the range at which you're buffering is plus or minus 1 pH. Okay, let's go to example 14. It says a buffer solution is made up of ammonia and ammonium chloride salt. Write the reactions for when you add acid or when you add base. Now the first thing you want to do is you want to identify what you have. And it looks like you have ammonia, which is a base, a weak base. And then you also have ammonium, which is the conjugate acid of that weak base. So notice how they look very similar to one another because they are conjugate pairs. When you add hydrogen ion, the part that will react with the acid, which is hydrogen ion, is going to be the weak base. So when we write a reaction for this, we're going to write it as a neutralization reaction. So NH3 reacts with the H plus to form, you're right, the conjugate acid. And then, of course, when you're seeing OH added, the conjugate acid is going to react with the base, hydroxide base ions. So we're going to show just that part, NH4 plus, not Cl, because it's going to be a very soluble salt here with ammonium in it. We know that's quite soluble. Plus OH minus, and when that happens, when that neutralization happens, you're going to see NH3 plus water form. And you're going, how did that happen? Well, when these two combine, you're making ammonium hydroxide. Ammonium hydroxide is going to dissociate, or spontaneously form ammonia and water. So this reaction yields ammonia and water in the end. In example 5, the first thing you want to do is just read it carefully several times if you need to, but I like to identify what I have, and I'm seeing a weak acid, which is called formic acid, and the salt, which has this part, but then I have the conjugate base with that weak acid. It says right here, it's a buffer solution. So once again, whenever I see the word buffer, I'm thinking to myself, Henderson-Hasselbalch equation. So I'm going to set up my Henderson-Hasselbalch equation, but I'm actually going to set it up with the specific ions or compounds that I'm dealing with. And so here's my conjugate base, which is HCOO minus, and then here's my acid. And that's what the equation says. Put your conjugate base on top, put the acid on the bottom. I'm going to need my Ka values. So before I think I'm given. Yes, I'm given my Ka. So I'm going to start off with pH equals negative log of 1.8 times 10 to the negative 4th power plus the log, and once again, I don't need it in volume, or I don't need it in molarity. I can put it in moles because that is how much reacts. If you put in molarity, you're more than welcome to do so. You'll see you end up with the same answer. So here's the moles. It's 0.60 moles of sodium formate and then 0.40 moles. And so you just plug it into your calculator and you should get your final answer, which is 3.92. And the thing about sig figs for logs is you add another sig fig from whatever you're logging. So if there's only 2 sig figs here, when you divide, there should be only 2 sig figs. You just add another sig fig, which means you're going to end up with 3 sig figs for both of your answers, okay? So log sig fig rules are very specific. Add one more sig fig from what you're, from the measurement that you're logging. So that was A. Now we go to B. B says if 100 milliliter of the buffer solution is diluted to a volume of 1 liter, the pH does not change. Why is that the case? Why does the pH remain constant on dilution? And once again, it's all about the moles, so it doesn't matter whether you dilute that solution. Of course, these concentrations will go down, but the ratio remains constant. Okay? So that is your answer. It's that ratio. It's the ratio of the conjugate base to the weak acid stays constant, even in a dilution. Okay, let's go ahead and go to C, reading the problem carefully. I'm taking 5.00 milliliter sample of a 1 molar solution of hydrochloric acid, and it's added to 100 ml of the original buffer solution. Now, if you recall, we made a 1 liter solution of the buffer solution, and so you're only taking a tenth of that. Again, this is 1,000 milliliters. This is 10 liters, so 10 liters is a tenth of 1,000 milliliters. And so everything is a tenth. So that means you only have a tenth of each of the moles that you see of the weak acid and its conjugate base, proportionally. So what I'm doing is I'm reacting this acid, I'm adding some acid to this buffer solution and seeing whether it can buffer the pH. And we're actually going to test to see what the pH is in the end and whether that is the case. Whether this buffer solution does buffer, prevent the pH from going up or down, in this case down significantly. So let's go ahead and set up a reaction. The reaction we're going to set up is a neutralization reaction, and we're seeing that the acid is going to react with which one? The conjugate base or the weak acid? You're right to say the conjugate base. This is what's going to buffer. The conjugate base is going to consume the hydrogen ions. So I'm going to write a neutralization reaction in an ice table because I see that there's going to be probably a limiting reactant scenario. So you've got hydrogen ions reacting with the conjugate base, which is HCOO minus. It's going to form the weak acid, HCOOH. I'm going to ice it, ICE, and I'm going to work in moles because there's a lot of things going on, and I'd like not to have to dilute each of my concentration. So the first thing I want to do is multiply these two, and I'm going to convert this into liters first. So multiplying liters times moles will get me a certain 0.00500 moles. And then, of course, how much I have originally that I'm reacting, let's see, I have 1/10 of this amount right here of the conjugate base, which is right here. What's 1/10 of this value? If you said 0.060, you're correct. That is 1/10. And likewise, I also, in this buffer solution, these are the two components of my buffer solution right here. And so we also have initially a certain amount of our weak acid, and it's 1/10 of that. What's 1/10 of 0.4? It's 0.040 moles. Okay, so now the reaction is going to occur such that the base is going to consume all of the acid, especially if there's a small amount compared to how much you have of the base. So a limiting reactant scenario plays out. And the stoic in these problems will be very nice. It's 1-to-1, so look at the change. The change is all 1-to-1-to-1. All right, and then of course at the end I have 0 amount here, and then I have less of my base, my conjugate base, and of course more of my acid as a result. And what happens at the end tells me what I'm going to do here. I have my conjugate base and its weak acid present, which means I still have a buffer solution, which means I can go back and reuse the same equation and substitute it all in. And I'm going to make it in a different color so I can contrast the equation and it doesn't blend in with the work here. So pH equals negative log of 1.8 times 10 to the negative 4th, this is pKa, plus log, and once again I don't need to turn it into molarity, I can leave it in moles, and so I'm going to put my conjugate base on top, and then here's my weak acid. So knowing your Bronsted-Lowry definitions of acids and bases is very important as you get into this unit for sure. So go and review. If you need to go back and review more, please review more of the acid and conjugate base, Bronsted-Lowry acid conjugate base model. So I do my ratio and I end up with a pH that is, and I'm going to pause to calculate this. All right, I got in the end 3.83, and then I used the definition of pH, and figure out what the H plus concentration is, which is the same as the hydronium ion concentration, and I get 1.5 times 10 to the negative fifth or fourth molarity at the end. Okay. Now you're going, what if you didn't have the hydrogen ion as the limiting reactant? What if it all consumed, or the limiting reactant was the conjugate base? So there was an excess amount of hydrogen ion. Well, that's what you would be using to calculate pH. It actually makes it an easier problem. If all that you have left is a bunch of acid and a lot more acid, H plus from the strong acid. So this H plus is the strong acid. This is the weak acid. This strong acid is going to predominate, and it's going to make up the pH. It's going to determine the pH of the solution. So in that case, the excess amount of H plus is going to discern the pH. And that's just a simple negative log of the concentration of H plus that's left over, and that will get you your pH. So you can still do this calculation if you didn't have enough of the base. But then that would mean there's no buffering going on. So the buffer solution wouldn't be really working. But you can see that the buffer solution is working here because adding that little bit of acid, notice how the pH only went down by 0.09, right? And so that is actually truly buffering the solution. You're really within the buffering limits, okay? Let's go ahead and do D now. In D, you're asked, you're given that you're taking 800 milliliters of a 2 molar formic acid and you're mixing it with a 200 milliliter of a 4.8 molar sodium hydroxide. And then you're calculating the H plus of the resulting solution. So you have a weak acid reacting with a strong base. Nothing to do with the buffer solution, by the way. You're not using any of the buffer solution, and you're calculating the H plus concentration of the solution. So once again, I'm probably going to do an ice table. I'm going to neutralize my acid with my strong base, my weak acid and my strong base. And I'm going to write a reaction that involves just the ions that are important. In other words, I'm going to do the net ionic equation to figure out what I have left over. Do I have more base or do I have more acid left over during that point in time? And whatever is left over is going to discern the pH of the solution, which is the H plus concentration. All right, I'm going to erase all of this so I have a lot of more room to ice it in the end. Hopefully you can pause and ensure that you have all this information. All right. So what I have here is the reaction. So here's my base, which is OH, and it's going to react with my acid. And remember, the acid donates the hydrogen to the base. So this hydrogen ion will go to the base to make water, leaving us the conjugate acid, or sorry, the conjugate base of my weak acid. So this is the neutralization reaction. You're going, but how did you know? Well, formic acid is this substance. And then sodium hydroxide, I know the sodium ion is a neutral salt. It's not going to do anything. So the hydroxide ion is what's going to react with the acid. And of course, I know what an acid is. I know what a base is. Acid donates a hydrogen ion. Base accepts a hydrogen ion. And so I know the result of this reaction. So it's just piecing out the definitions and using my knowledge of the Bronsted-Lowry definition of acids and bases. So the first thing I'm going to do is I'm going to multiply my values together between my acid, or the molarity and the volume. And I can turn this into liters. So 0.8 times 2. 0.8 times 2 is 1.6. So this is 1.6 moles of my acid. My base, likewise, I'm taking 0.2 times 4.8, and that will give me my moles, and that's 0.96 moles of my base. I can see who the limiting reactant is. The limiting we start off with 0, these two. Your limiting reactant is the least amount, and these coefficients are so nice. There's 1-to-1 coefficient, so you can see who the limiting reactant is. It's this sodium hydroxide. And I'm going to subtract that limiting reactant amount. And of course, I'm going to add that amount over to here. Again, the ratios for these problems are amazingly nice for you all. And the limiting reactant, I'm going to have an excess amount of acid, 64 of it, okay? Now, water is not so significant because it's a liquid, so it's not anything that might be important for me, but I know water's neutral, so I can actually put that in if I wanted to. But the important ones are the ones, what will change the pH in essence is going to be your anything that is your acid or base left over. Okay, so let's take a quick assessment as to what we have at the end of this reaction. I have some weak acid, which is called formic acid. And guess what? I have the conjugate base of my weak acid. So I've made a buffer. This is a buffer solution. Weak acid, conjugate base. Water's neutral, weak acid, conjugate base. So identifying those pieces of what makes a buffer solution is very important. And so to find my pH of this buffer solution, I'm going to go to Henderson-Hasselbalch equation. So I'm going to take the negative log of my Ka plus the log of my conjugate, and I can keep this all in moles without having to divide it by the total volume, which ends up being 1 liter, by the way. It's 1,000 milliliters. 800 plus 200 is 1,000 milliliters, which is 1 liter. So then I do my conjugate base on top, which is 96 moles, and then my acid on the bottom. So I've created what is called a buffer solution by reacting some of my weak acid and a strong base. pH ends up being, and I'll pause. I finished the problem on the side because it was mathematical from there on out. And once again, to find the H plus concentration is just to take 10 to the negative pH. And when I do that, I end up with 1.2 times 10 to the negative fourth molarity for the concentration of hydrogen ion or hydronium ion. One in the same concentration in the end of the same substance, okay? It is very important to work through these supplemental worksheets that I have for you because these worksheets are in fact a lot of just redundant practice for you to get the idea of what a buffer solution is. It's always, once again, a buffer is a weak acid and its conjugate base, or a weak base and its conjugate acid present, okay? Or a weak acid and a weak base, so two different acids and bases. What I'd like you to do is do FRQ number 4 and 5. Finish up 6 and check your answer and follow through with number 6. Continuing on to number 7. When we worked through example 15 together in part D, what we were reacting was a weak acid with a strong base. And that happens oftentimes in this method called titration. So we're getting into acid-base titration. We're reacting an acid with a base of some sort. And so here's what a titration setup looks like. You've got a ring stand. You've got a burette, which is a very fine, precise measuring tool for volume. So it's measuring a certain solution, and it's called a standardized solution because it's a known concentration. So this is standardized means known. So we know what the concentration of this acid or this solution is. And the known molarity, by the way, known molarity. And then, of course, we have what's in the Erlenmeyer flask, which is our unknown molarity. So we don't know the concentration of this solution. And so we're titrating a known against an unknown, which is very common of what we do in chemistry. We usually will test knowns to understand our unknowns from that. We tend to add an indicator in order to hit a visual a visible point called the endpoint. And this endpoint is, we hope, where the equivalence point is, which is when the moles of acid is equal to the moles of base. Let's go ahead and define titration. So it gave you a little bit of a introduction into the setup. It's a process of finding the concentration of an unknown solution by gradually adding a standard known solution to the unknown solution until endpoint is reached. We hope that the endpoint is the equivalence point where the moles of acid are equals to the moles of base. So let's take a look at this equation. This equation certainly should make sense to you. It's very similar to the dilution equation, but instead you see acid on one side and then base on one side because you're looking at the moles of acid equaling the moles of base. Now, if you recall, molarity, once again, always this idea of what molarity is. Molarity is times volume gives you equals moles. And so that is what you're seeing. Sorry, it looks like it's not equal to, so let's rewrite that. M times V equals moles. So if you have acid here, you're talking about the moles of acid on one side. And likewise, it's also the moles of base on the other. Now, what is this all about? It's actually looking at the acid and seeing if it's monoprotic, diprotic, or triprotic. Likewise, for the base side, you're looking to see if it's monobasic, dibasic, or tribasic. This accounts for the stoichiometry. When you do stoichiometry, it actually eliminates having to do any kind of stoich, and it makes it easier for you to be able to concentrate on that equivalence point. The standard solution is usually in your burette here. It's a solution whose concentration is accurately known. It's also called the titrant, so we also call this standardized solution the titrant. And I'll write that in our diagram just to remind us. Titrant, we also call this. Let's go ahead and do something called standardization. So we're going to do a problem that involves standardizing a solution. And we're going to work it out together. So let's start off. It says, for standardization titration to determine the precise concentration of the titrant, in this case NaOH, which is sodium hydroxide, we use something called potassium hydrogen phthalate. It's this huge ionic substance. It's labeled or abbreviated KHP, potassium hydrogen phthalate. The molar mass of this big ionic compound is 204.22 grams per mole. And we use this substance for several reasons. It's a stable solid. It's ionic, which means it's a stable solid. It's monoprotic. So the stoichiometry is 1-to-1 between the acid and the base. So the base that you're trying to find the concentration from and the acid is easily reacting on a 1-to-1 ratio. In this example, what we're seeing is 252 grams, 0.8 milligrams of KHP were dissolved in water and titrated with NaOH. So here's my known amount of my acid. Here's what I'm trying to standardize it against to figure out what my exact concentration of my base is so that I can put it into this known or this burette so that I can standardize and figure out my unknown, completely unknown concentration. So you're taking another known and figuring out what the concentration of this titrant is so that you can titrate it with a completely unknown substance in the end. So it says it requires 21.67 milliliters to reach equivalence point. What is the molar concentration of the NaOH? So I know the NaOH and the KHP are reacting 1-to-1 ratio-wise. So the first thing I want to do is convert this to moles. Exactly. So I can knowing that, I can then ratio it against the NaOH, which is 1-to-1. It's quite an easy ratio. So following along, this calculation, the standardization process is very, very simple, honestly. So the first thing you want to do is convert your milligrams and convert it into grams, because I really can't convert it into moles until I get to grams. So I'm going to do milligrams on the bottom, 1 gram on the top. And then I'm going to use the molar mass. So I have 204.22 grams of KHP. But then I'm also going to ratio it with NaOH. So a mole of KHP, it's a 1-to-1 mole ratio, which is lovely. And then from there, I have the moles of NaOH. That's exactly what I want to do, is find my moles of NaOH, and I know the volume at which I reach. That's how much NaOH I'm going to add to reach the equivalence point. So then I can just divide it by that volume in liters, of course. So I'm going to convert that to liters really quick. Moving it over 3 spaces to the left. So dividing all of these numbers together, I get, and I'm going to wait this out, okay? So dividing it by 1,000 and also 204.22. I get a very small number, and this is 0.00123, like 8. I'm going to stop there in the moles. And it's moles of NaOH, okay? Now I'm going to divide that by the liters of NaOH, which is 0.02167 liters, and that will get me my concentration of NaOH. And the concentration of NaOH ends up being 0.05, and I'm going to sig fig it with the measurement, which is 21 point, so I'm going to force sig fig, okay, 712. And this is the molarity of NaOH. So this is how you go about standardizing and calculating for the solution. It's a very easy calculation. You're using a very stable monoprotic acid to titrate it with NaOH, and that will give you the concentration of NaOH that you know. So it's your known concentration. And I'll put that in parentheses, that this is your known concentration. Okay. Now we also need a pH meter sometimes when it to be more precise. Rather than using an indicator that changes color, we can use a pH meter to determine the pH at the equivalence point. It's more accurate than indicators. Acid-base indicators are very, it's a qualitative way to determine the endpoint or the equivalence point. So the color indicator, it's used as a color indicator to detect the endpoint. An endpoint is when the indicator changes color. Usually it's the same point as the equivalence point. There's a transition range though, so that's why the endpoint isn't as quantitative as a pH meter, because there's a transition range. And the transition range it varies with each indicator that you're using. It's when color change occurs. Some of the most important characteristics of pH indicators is that they're either weak acids or weak bases, and there's an equilibrium involved in that weak acid. So I'll show you what I mean by equilibrium. The pH or pKa or pKb of the indicator equals oftentimes the pH at the equivalent points. At the equivalent point that the color change occurs, when the color change occurs at the equivalence point. There's a distinct color oftentimes in the equilibrium reaction for the unionized on one side of the equation, and of course for the ionized for chemical species on the other side of the equilibrium reaction. Oftentimes the pH range of the indicator must align with the equivalence region. So let's look at an example. By reaching the equivalence point where the moles of the acid or base can be determined, and if you weigh the unknown acid or base, the identity of the acid or base can be calculated via its molar mass. So in essence, you can also identify an unknown acid or base if it's a solid and find its molar mass in the end. So here's an example of an indicator. This is called phenolphthalein. You're actually going to do a lab based on this indicator. It's a weak acid indicator, and it has this formula that you see, but it's really an abbreviation because the IN stands for indium, and it's really a large molecular species. But to abbreviate makes it easier for us to see this equilibrium reaction. Notice the arrow going both ways, and you're seeing it ionize. It's a weak acid. So this is a weak acid ionizing into its conjugate base that you see here, and of course the hydrogen ion. Now, if you notice, if the equilibrium shifts forward, if it shifts forward for this indicator, what happens is the solution turns pink because of the indium present, this ion right here. Now, if it shifts reverse, what happens is the pink gets consumed, forming more of this molecular species of the indicator, which is clear. So you'll see the solution turn clear quite rapidly. So depending on where the equilibrium lies, this indicator will turn pink or clear. So let's take a look at this indicator on the indicator chart that you see here. So oftentimes when I look for an indicator, I'm looking for the pH range. So the pH range at equivalence point is between 8.3 and 10 for this if you were to use this indicator. And once again, if it's greater than 10, you'll see a dark hot pink color. And then if it's less than 8.3, you're going to see a colorless. And that's why the indicators are used in chemistry classes. It's not the ideal quantitative method like a pH meter is. This gives you, I mean, you're really hitting between a large range of pH when it comes to an indicator. So you're really, it's going to be hard, you're going to have a hard time reaching exactly where that equivalence point is because you're using any of these different indicators. Okay? Let's go ahead and understand how indicators work and answer these questions for you to understand how they work. So it says through here in example 17, the pH of a solution is 9.8 when endpoint is reached. What acid-base indicator would be appropriate for identifying the endpoint? So what I want is I go to the pH range and I find indicators that hit that range of 9.8. So phenolphthalein obviously hits that point. I'm going to keep on going until I find any other ones that hit that point. It looks like that's the only one. So I'm going to choose this indicator, phenolphthalein. And why I choose that indicator is because of the pH range. So this phenolphthalein is best, and that's because it has a and I'm going to put because shorthand this because the pH range is consistent or aligned with the endpoint, which is 9.8, pH of 9.8. Okay, let's go to the next one. In number example 18, in a titration, one group of students used methyl red as the indicator for example, that should say example 17. Okay, so example 17. And then, could this indicator be appropriate for the solution? So I'm going to go to methyl red on the chart, and I'm going to see if that would be appropriate. No, it wouldn't be. So what color would you expect would be given at that pH? So at 9.8, methyl red would turn, well, it's on the base end of this, so it's going to be turning yellow. So the color would be yellow in the end. And you're going to explain your reasoning with the fact that on the base range of this pH range is yellow for methyl red. So the base range is yellow. Okay, that will be your explanation. I'm going to let you write that out as I verbally explain it. Now, why don't you pause and see if you could do example 19 and 20, and I will explain it after you unpause. So hopefully you've had a little time to work through example number 19 and 20. I will go over it with you just to make sure you understand it. The acid-base indicator would be appropriate for the pH of the solution that's 5.2. So I'm looking for a pH of 5.2, and there's several actually when endpoint is reached. There's actually, you can use litmus because the pH range is within that 5.2. And then you can write down the range, of course, 5.0 through 7.0. There's also methyl red you could use, and the pH range is 4.8 through 6.0. You can also use bromocresol green, which is 4.0 to 5.6, and that's it. So those are the three possible indicators you can use for that specific titration if you're using if you're doing titration with it. Now we have a buffer solution with a pH of 2.2 is tested with bromothymol blue. So I'm going to go to bromothymol blue, and I see the pH range is that pH is way lower than the pH range, which would turn it green, by the way. And so I know that it's probably going to turn it yellow, bromothymol blue. Yellow is what I would see. Now, I forgot to mention, and it is very important to mention, that the pH range is usually the color contrasts or the color blending of the two acid color versus the base color. So what does blue and yellow make? Green. What does colorless and pink make? Well, light pink, as you see here. What does red and yellow make? Well, red and yellow makes orange. So be aware that the pH range is really what's happening is it's where the equilibrium hits. And that's why you see both your reactants and your products present during that time. And that's why you see the two color blends. Blending the two colors will give you your equilibrium color, which is your pH range color. Okay? And you can go through all of them and you can see how they all pretty much is based on this equilibrium between the reactants that has a certain color and then the products which has a certain color. And when you hit equilibrium, obviously you have a blend of both reactants and products. You will work through, now that you know what acid-base indicators are, FRQ 8 and 9, and get through all these indicator questions. Here's a little bit more space to spread out in terms of your work for this FRQ, and check your answers at the end. We are going to get into titrations, and there are three types of titrations we're going to look at. And the first one is a strong acid and a strong base. So you have both strong acid titrating with a strong base. Here's your strong base, and here's your strong acid. It looks like you're starting off with your base and you're adding your acid, as it says right here. You're adding some acid at a time. So now if you think about that, actually you're adding base to your strong acid. So that's why the pH is low right here for the pH curve. And then, of course, as you add more and more base, what happens is more and more of the acid gets consumed by the base until you hit this equivalence point. And for a strong base and strong acid titration, the equivalence point is where the pH is 7. And that's why most people will think, most students and most people in the world will think that the pH is always 7 when you're dealing with any acid or base situation, but it does depend on the strength of the acid and base. But at this point, your moles of acid equals the moles of base, and this is called the equivalence point. Notice this is the inflection point. The inflection point is when the concavity changes, just a reminder, and this is the point at which it changes, the midpoint of that. To draw what you are seeing in this scenario, I would draw however many acids. So I'm going to make my acids red, and then I'm going to make my base blue. So here's my base reacting with that one, and then of course here's another base reacting with that hydrogen ion, and here's another base reacting with the last hydrogen ion. And this is when the pH ends up being 7, because all you have is water. And we know water self-ionizes, so let's talk about that. Water self-ionizing. So this is water, here's another water molecule, and here's another water molecule. So you only have water in the solution. When water is present, it self-ionizes into equal moles of hydrogen ion and hydroxide ion. And when that happens, we can set up what is called an ice table to see how much you have at equilibrium, because we know Kw. Kw for water is for 1.0 times 10 to the negative 14th. So we show the ionization. You start off initially with 0 amounts of both the products, and then some of it ionizes. We don't know how much. And then you're forming both your products here. But we don't care about what happens at equilibrium for this substance because it is a liquid. Pure liquids do not affect equilibrium. But we do want to know how much ions are present at equilibrium. And so we set it up into this K, the H plus concentration at equilibrium and the OH concentration at equilibrium. And then we multiply them, and that ends up being x times x. So this is x times x, substituting into the Kw expression. And that equals 1 times 10 to the negative 14th. And we find out in the end that when we multiply it all out, or square root this value, you end up with 1 times 10 to the negative 7th for the H plus concentration as well as the OH, which is also equal to the OH concentration. So this is my X basically. And my X is the same are these two substances right here. When I do that, I then take my negative log to find the pH. So I'm interested in finding the pH. Negative log of the H plus concentration, which is 1 times 10 to the negative 7th, and voila, you have the pH of 7. This is where you get this 7 value, is through water's self-ionization. So water, the pH of there is a pH of 7 at the equivalence point due to water self-ionizing. And this is the math behind it. Now, unlike a strong acid, strong base titration, here we're dealing with a weak acid, strong base titration. And what I'd like to think of it as the stronger one predominates at equivalence point than the weaker one, and that's true here. That's why the pH is greater than 7. But really there's a lot of things going on inside in the background picture that you have to really do understand why the pH is greater than 7 at the equivalence point. And that's what you're seeing here in this specific titration. So who's your strong base? Right here is your strong base, sodium hydroxide. Here's your weak acid right here. And so in this example, what you're seeing is your weak acid is being titrated with your strong base until it hits the equivalence point right here. And notice the pH is greater than 7, as you see. Now we go to the third type of titration, which is a strong acid with a weak base. In this example, here's your weak base. Here's your strong acid. Notice you do have to recognize your strong and weak acids and bases. So you're titrating your weak base with your strong acid. And in this case, actually you're titrating a strong acid with a weak base. And so you're adding more base and it's becoming more basic until the equivalence point. And at that point, what predominates? Usually the strong. In this case, that's why the pH is less than 7. It's 5.28 at the equivalence point. Okay. So we're going to be looking at mainly these two types, and we're going to look at the background understanding, the very depths of understanding why the pH is greater than 7 at the equivalence point or less than 7 at the equivalence point for this type of titration between a weak base and a strong acid versus a weak acid and a strong base. Before we go into that, we should understand polyprotic acid. Poly means many. Protic means protons, so it's the hydrogen ions. Protons are your hydrogen ions. They're just a single proton floating around, no electron. And so we're talking about many hydrogens. So it's a polyprotic acid. It's an acid that donates more than one hydrogen ion. In a titration, the number of inflection points depends on that number of hydrogen ions. So we're going to probably see multiple inflection points based on however many proton that substance can donate or react. So here's a monoprotic. Mono means one proton. So we're looking at this is one proton. Notice only one hydrogen ion. Diprotic means two protons, and so notice how there's two hydrogen ions for this acid. Triprotic means three, and so there's three protons here for this acid. So in a polyprotic scenario, like you see here, it looks like you're titrating with strong base. So it starts off with the weak acid, and it looks like it's a triprotic acid. And you'll notice you'll probably see three equivalence points, okay? So three inflection points. So the first one is, so you start off, there's a buffer solution going on here. As I add more base, notice it's not really changing in the pH much. And then all of a sudden you get to your first inflection point, which is your first equivalence point. This is when the first hydrogen completely reacts. The first hydrogen gets pulled off completely. And then you get to this halfway to the second halfway to equivalence point, which is this right here. Now you're still buffering, by the way. You're buffering, and then an inflection point is when the pH changes quite rapidly. So this is the second equivalence point. So it's two hydrogens being pulled off now or completely reacted with the hydroxide ion. And then you go through another buffering, and the third one is just not as sharp. So this is the third inflection point right here. And that's where you see three inflection points for the fact that you have to neutralize with all three hydrogen ions that you see with the NaOH that you are titrating it with. Go ahead and work through this example. I think it is a standardization. We've done a standardization problem already, and we can probably, from here, you can probably figure out molar mass of an acid if we're looking at an unknown acid and a solid acid specifically. So that's why you can mass it. So hopefully you can kind of problem solve and work your way through this problem. Work through FRQ 11 and 12 into 13 and 14. And then we will do a full-on titration. Example 21 is an extensive full-on titration for you to understand how we go about creating this pH curve right here that we're going to create for this titration, which is what you saw earlier in the triprotic acid as it was being titrated, the phosphoric acid being titrated against the sodium hydroxide. Right now we're going to look at very simple one, a monoprotic acid, weak acid, titrated with a strong base. Okay, so this is a weak acid, strong base calculation, and we're going to do a complete titration. And it says on paper, and you're going to probably print it out and do it on paper, but it's you're doing pH sampling as you go through each titration. Okay, let's go ahead and begin our titration. Now, what's in our flask is some acid, and the acid we have 25 milliliters of a 0.10 molar acetic acid, and I'm going to call this acetic acid HA. You can see the hydrogen ion that's in this acid, and it's monoprotic. It's titrated with some base, and the base is sodium hydroxide, 0.1 molar of that sodium hydroxide. You're given the Ka of the weak acid, and so we're going to proceed from there. Initially, when you haven't added any of the base, this is before the equivalence point, and you haven't added any base. All you have is the acid. So what you're going to see is the acid, which is HA, acetic acid, ionizing in water. And when you ionize acetic acid in water, you'll notice it's reacting with water. Sorry, when I say ionizing in water, it is basically water hydrolysis of the weak acid, which means you're breaking up with water the weak acid. And that's exactly what you're doing. You're breaking it up. And as a result of breaking up the weak acid, you're forming hydronium ion because the acid, Ha, is broken up and dissociated and ionized into A minus and H plus, which is H3O plus because there's water here. So identify who's the acid and who's the conjugate base is really important. Once again, the Bl acid is going to be here. The Bl base is right here. This is the conjugate acid, and this is the conjugate base. Knowing that can help you to really maneuver through how the reactions are taking place, what is reacting with what. So here you have only the acid, and this is the concentration of the acid, and you have none of the ionized parts of the acid present initially. A change occurs. Some of the acid will dissociate and ionize, and we know that it's going to be a very small amount. And then, of course, we're forming equal moles of the hydronium ion and its conjugate base. So the conjugate acid and the conjugate base. As a result, we then add these two columns. We end up with this 0.10 minus x. We don't care about water because water is going to not affect equilibrium. And then, of course, the two ions that make up that. The two ions that make up this acid here. Now, notice we're always considering the aqueous ions or the acid here. So when we write the expression, it's products over reactants. Now you'll notice that I put, instead of hydronium ion, I put hydrogen ion. This makes it easier for me to see that these are the ions that make up this acid right here, Ha. So products over reactants. This is called the Ka. So this is the equilibrium constant for the acid. A is acid. And so Ka is given to us as 1.8 times 10 to the negative fifth. I substitute all my equilibrium amounts into my expression. And then what I'm going to do is assume that X is small because very little of the acid amount is going to ionize. So this is very, very small because it's a weak acid. And because of that, now I can take that number, that term right there and make it equal to 0.1. And solving for x, I get my x. And I know x is my H plus concentration, which is hydronium ion concentration. And I end up being able to find the pH of that. So I take the negative log on both sides, and I get a pH of 2.87. So really, if you look at your pH curve and notice the x-axis is the volume of the base, we haven't added any volume of base, so we're at the 0 mark here. The pH turns out to be 2.87, which is right here, when we haven't added any base. All we have is the acid, and that's why the pH is less than 7. It's 2.87 is acidic. Okay. Now, you should check your assumption to make sure that the assumption method is valid. So you're validating. So you're calculating percent ionization, and so what it is just the amount of X, whichever X is, which is right here, divided by the total amount of the original concentration of the acid, which is 0.1. And dividing those two and timesing by 100, you get 1.3% that ionize. So this is how much ionize, only 1.3% of the amount that you see here. Ionize, which means it's a good assumption. It's less than 5%. Anytime we're less than 5% of the original amount, you have made a valid assumption. Thus, you are able to zero out that X and make this equal to 0.10 rather than 0.10 minus X. Notice that notice with only acid present in solution, the pH is acidic in the end. let's go ahead and draw draw a particulate drawing of what is happening inside the solution. So it looks like we're adding HA. We know that there's just water in there, so I'm just going to add one particle of it. And so I'm going to produce H3O plus and A minus. And that's what you're seeing. But a lot more in here is made up of HA. So a bunch of HA molecules because they don't ionize that much. All you have mostly in here is a bunch of HA and only very few of the HA will ionize into the two particles, which is hydrogen ion and A minus. Let's go. Now in this example, we're adding 5 milliliters of a 1.1 molar of sodium hydroxide to the acid that I have in the Erlenmeyer flask. So this is how much acid is in the Erlenmeyer flask. Because I'm reacting a weak acid with a strong base, I'm going to see a neutralization reaction occurring. And in this neutralization reaction, the acid has a hydrogen ion, is going to transfer, and I'm going to make it, I don't want to block the hydrogen ion. The hydrogen ion is going to donate a hydrogen ion over to the base hydroxide ion to make, in essence, water. And that's what you're seeing in the conjugate acid of this weak base. Now, when I react this, I multiply. I'm going to work in millimoles. So multiplying these two values, I get millimoles of 0.5 millimoles. Now, remember, recall from the original, I have, this is the amount of acid I have in the Erlenmeyer flask. And so multiplying these two, I get 2.5 millimoles. The limiting reactant, you can see obviously, is the hydroxide ion. And so you're going to subtract that amount. And of course, you're going to make some of this. Now, why did I zero this out? Because I don't care about water. Water's pH is 7. It's not going to, in the end, that's not going to have bearing on overall my solution. The pH overall of my solution, unless all that there is water. And then you can look at it strictly of water. So here's zero this. You're going to make equal amounts because everything is stoichiometrically 1 to 1. So it's a nice 1 to 1 ratio here. Your limiting reactant runs out. Your excess left over is some of the acid and its conjugate base. And so if you can think of it really closely, or if the light bulb turns on, this is truly a buffer solution. The weak acid and its conjugate base present. So my mind goes to the Henderson-Hasselbalch equation, and I'm going to plug everything into that equation. It's as simply as that. You do your pKa, which is negative log of your Ka given to us in the previous, and then you just ratio the millimoles. You don't even have to convert to molarity. You can ratio the conjugate base on top and then the acid on the bottom. And that's what you're seeing, conjugate base and then the weak acid on the bottom. And then I get my pH. And notice at 0, it was 2.87. And now at 5 milliliters, the pH is going up. So I'm adding milliliters of base at a time. And I'm going to see this curve create the pH curve that you see. So the pH ends up being 4.14. And then this explains why it becomes a buffer solution. I'm going to draw microscale what's happening, and I'm going to do it as best I can with these fraction of values. What do I mean by fraction of values? Like half a mole, you know? So I'm going to do it just relatively proportional. So here I am adding base, and the base I'm adding is hydroxide, OH minus. Now I'm going to have 6 HA molecules in here. Now I know water is also in here, but it's just a part of the solution. So 6 HA. Now if I add one of these is going to consume one of the HA. And so I'm going to show that consumption by circling them together and forming, as a result, they're going to kick out the conjugate base, which is A minus. So one of the A minuses will be kicked out. So water forming out of this, H2O, and the conjugate base getting kicked out of that. Okay? So now I go to the next example. In the next example, now instead of 5 milliliters, now I've added 5 more milliliters, giving me a total of 10 milliliters added. We're still before equivalence point. Once again, it's also a neutralization reaction. It's the same reaction that you see in the ice table above. And you can see who the limiting reactant is. So hydroxide ion is still the limiting reactant. So I'm going to react those amounts, 1.0 millimoles, and then I'm going to form that amount of the conjugate base. And again, I have what is called a buffer solution once again. Utilizing my Henderson-Hasselbalch equation, I'm plugging those amounts in, of course changing the millimoles of what I have of the conjugate base and its the weak acid. I plug it in and I get my pH of my solution at 10, and I'm going to record it on my pH curve here. So after adding 10 ml of the base, I'm at 4.57. So it's barely moving up just a little bit. And that's because we have a buffer solution. Buffer solutions actually resist changes in pH as a little bit more acid, or base in this case, is added. Now, what will this look like? Well, now I'm adding twice as much of the hydroxide ion. So I'm going to show that I'm adding 2 of them. Okay. Now, if I'm adding 2 of them, and I have 6 of these HA molecules in here, 1, 2, 3, 4, 5, and then 6 HA molecules, 2 of them are going to get consumed by that hydroxide. 2 of the HA molecules is going to get consumed by the hydroxide, kicking out, and I'm going to make the bases blue, 2 of these A minuses. Now the ratio, notice the ratio of HA is still more than A minus, right? There's 4 of these compared to 2 of these. And it's pretty much not the same ratio, but it's, let's see, this is 3 halves. 1 divided by 3 halves is 2/3. So there should be, for every 2 of the A minus, there should be 3 of these HAs. So I guess I should have been a little bit more vigilant of the amounts. But it's okay. You see the difference, though. You see more HA than there is A minus. That's why this solution is still acidic. You're always looking to see what is still causing it to be acidic, and there's more acid than the conjugate base present. Now, we go to this next scenario where we're adding about 2.5 milliliters more. We set up an ice table, same thing. We notice that at this point, though, you're subtracting 1.25 millimoles as the limiting reactant, but at the end of this reaction, this limiting reactant reaction, you're going to have equal moles of both the acid, the weak acid, and its conjugate base. And so this is maximum buffer capacity. We call that when you have equal amounts of both the weak acid and its conjugate base. That means it can buffer both ends. Either if you add more acid or if you add more base to this solution, it can do buffering on both ends. And so that's why we call this a maximum buffer capacity. And notice how the log of 1, this becomes 1 as a value. Log of 1 ends up being 0 here, so the pH equals basically the pKa during this time. And again, noticing the pH after adding 12.5 milliliters, the pH doesn't go up that much. Once again, great buffer. It's a great buffer. And so in your solution, I'm going to show this actually works perfectly. I made it so it worked perfectly. So here I have 3 hydroxide ions added together, or added into the solution. I'm going to say OH minus, OH minus, and OH minus. Okay, now it's going to consume, oops, I really wanted to make that red. It's going to consume your HA molecules. And when it consumes the HA, it's actually going to consume 3 of them. So I'm going to circle the 3 that gets consumed. And then I'm going to show the 3 conjugate bases that are going to come off of that. So 1, 2, and 3. And notice this works really nicely, how there are 3 of these conjugate bases and 3 of these acids in this reaction. And thus the ratio is the same. 1. The ratio of this conjugate base over weak acid is going to be 1. So I made it so that there was a perfect amount at the equivalence, or sorry, at halfway to the equivalence point. This is actually halfway to the equivalence point. Okay, so now we're adding a little bit more of the base. I think we're adding from 12.5 to 20. That would be about 7.5 of the base. And so let's see what happens. It's still the neutralization reaction. And at this point, you're going to see actually and the limiting reactant is still sodium hydroxide, which is the hydroxide ion. And we're going to subtract, but now you're seeing less of the acid present, a lot of the conjugate base. So notice how there is only 2 HA. All of these are becoming water, and of course you have 2 HA and a lot more of the conjugate base, A minus, present in solution. And so that will predominate, and that's why the pH gets higher and higher, even more higher, because there's more base, conjugate base present. But it's still buffering, so notice it's still slowly changing the pH at this point in time. So this next point is when the pH is 5.35. Once again, still buffering, but the solution is becoming more basic because of the presence of a lot more of the conjugate base than the weak acid itself. Now, this next point. This is an important part. This is the point called the equivalence point. When you react your acid and your base and you multiply your amounts, you'll see that you have equal amounts of acid and base during this time. So who's your limiting reactant? Both of them are going to be limiting. So both reactants are going to run out, leaving you with a whole bunch of conjugate base here. And so nothing left, some water present for sure, but the conjugate base is what our focus is going to be. So now we know that the conjugate base of a weak acid is quite stronger. Now, stronger than who? It's actually stronger than water. So it undergoes a reaction with water, and it hydrolyzes with water, like you see here. And I did forget to write it as an equilibrium because it is an equilibrium reaction. So you're hydrolyzing with water, and you're forming, and it's an important point to make that it is an equilibrium. So this conjugate base is going to hydrolyze with water, and it's going to form your weak acid again and hydroxide ions. So this is the important part. This is what's actually going to discern your pH in the end, the hydroxide ion. So now, in this case, since this is a Kb scenario, this reaction is about equilibrium and it's Kb, I have to figure out what the Kb constant is. So I'm going to take Kw divided by Ka to figure out what the Kb constant is. And since this is a Kb reaction, I'm going to do, it's because I see hydroxide ion being produced. I'm going to do products over reactants as I see right here, excluding the pure liquid right here. I do not include water. And that is going to be my equal, and I don't know how much, by the way, ionizes. So I'm going to use the Kb to figure out how much of this, how weak this acid is, and how much of it ionizes in the end. And that will discern how much hydroxide ion will be present also, which will help me to figure out the pH. So I divide and I use my Ka expression into this, and I solve for x in the end. And of course, I do assume x is small, so I do have to make sure I do percent ionization to figure out how small it is. And it's quite small later on, you'll see. And as a result, my pH, sorry, my OH concentration is this value, and then I take my negative log of that, and that will give me my POH. And I take 14 minus that will give me my pH. So at this point, you're seeing a shoot up of the pH. The pH just really sharply increases at this point. Notice it lifts up. The slope is really sharp here. And again, you want to validate and notice how weak this acid is. It's quite, the conjugate base right here is quite a weak acid. It ionizes very little, and that's why the percent is so low. It's definitely less than 5%. And to describe this, you see a sudden increase in pH. In other words, the inflection point at the equivalence point. This is equivalence point because the moles of acid equals the moles of base at this point. And the presence of the conjugate base of the weak acid and its hydrolysis in water is what causes the pH to be greater than 7, which means it's basic, rather than the misconception that it would be neutral at equivalence point. And so what we will see at this point, class, is your solution with phenolphthalein added as the indicator is going to be this light pink. And so we know that we're at equivalence point because even though these solutions were all clear, you didn't see color, not until you see this here where it's light pink. So if it's equal moles of acid and base, that means for every HA molecules I have, and I said that I would start off with 6 of them, that means I'm adding 6 base, 6 hydroxide ions into this solution. I'm going to line it up, okay? Actually, I'm going to make it in 3s so you can see the 6 pretty easily. Okay, so when you add it all up, you'll notice that they all react. And when they all react together, all that you're left in the solution is a bunch of A minuses. How many? 6 of them. And be aware that this HA has all been consumed to form water and these HA molecules, okay? Or sorry, A minus, the conjugate base of your weak acid. And there will be 6 of them. Okay. Now, this is a very important point, by the way. The equivalence point is very important because now you have to understand where that pH is going to come from. It's all because the conjugate base and that amount of the conjugate base present is going to ionize in water, producing this hydroxide ion, which which determines what the pH in the end will be. So now we're adding a total of 30 milliliters of the base into your acetic acid solution. 25 milliliter of the 0.1 molar acetic acid solution. So really we're after the equivalence point from here on out. And so it's still a neutralization reaction. So what you will see is an excess amount of your strong base, which is OH minus here. And when you do your ice table, you'll notice that your limiting reactant now is the acid, and you're left with a lot of excess base. And that excess base simply is going to discern, or that will determine the pH. So you're going to total up the volume, which is 30 ml, plus the 25 ml from the acid. So that's the total volume of the solution, and you just calculate the pH from that. You're wondering then, what about this conjugate base, Mrs. No? Well, this conjugate base is quite weak. We already saw how weak it was. So really what predominates is a strong acid that is in excess during this point in the titration. So although it may contribute just minimally, this is the significant contribution. So we're going to call this a negligible contribution as far as to the pH of the solution. This is what's going to cause the pH of the solution. And that's what we're going to do. We're going to take the negative log of that concentration, and we will see the POH or pH to be really significant at this point, past the inflection point, obviously. So this is 11.9 when we add 30 ml. Again, I'm just creating this titration curve along the way. Now, with an excess amount of the strong base, not the weak base, this will determine the pH of the resulting solution. What your indicator will show is this hot pink color. Okay, I'll try to write over it. I hope the red really shows through it, but we'll see. So now instead of, let's say, instead of 6 hydrogen ions, let's just say that there's 7. Okay, 7. And I'm gonna draw the hydroxide ion a little bit simply by saying 7 of these, okay? So imagine 7 of these, and of course we had 6 of the HA acid, right? The weak acid. So 6 of these. Oh, yikes. You cannot see it very well. So you can imagine, how about I write it on the outside? I really wanted the hot pink there, so I'm going to write it on the outside so you can see. 6 HA molecules. So you know that with the 7 and 6, all the 7 gets consumed, leaving us with 1 of the hydroxide ion, and that will be able to, and of course, that will make us 6 A minuses, so there's going to be 6 A minus in there. That would, and a bunch of water, but that the pH is going to be dependent on this strong base right here. So that's where POH is calculated, and then you'll get your pH. And of course, now instead of, and you keep on going, honestly, with all your calculations. So now in the next step, you're adding 8 OH minus ions. Still you have 6, right, in here. So 6 HAs. And of course, you still have 6 A minuses. You can't have any more than however many HAs you have. So from that, all of this reacts, and you're left with only 2 hydroxide ions, and that will cause the pH to go up, and that excess amount is going to determine the pH. I keep on saying discern, but determine. So you're seeing that the limiting reactant is still the acid, and the excess amount of hydroxide ion will determine the pH in the end. That's what we're going to use to calculate the pH. And again, you just plot these points as you go and calculate. In this instance, you're looking at 9 OH molecules or ions. Still 6 in here of the HA, and of course you're making A minus, so you're reacting all of that. You're left with 3 hydroxide ion, and that excess amount is going to cause the pH to go up a little bit, or a lot more, or sorry, a little bit more as you go through. So this ends our titration class. You've gone through a full titration, and that full titration gives us a pH curve that looks ultimately like what we recognize here. And we can identify the inflection point by looking at the sharpest increase. And so this is where the equivalence point is right there. I'm going to work through example 22 with you all so you can see how I go through this FRQ. Okay? The first thing you want to do is read the problem. Read it several times. You see a weak base. This is the weak base that's being told. And label what you can. If this is your weak base, you know that this is your conjugate acid, and this must be your weak acid, and this must be your conjugate base. So you have all the pieces of what is called the Bronsted-Lowry definitions of what an acid and base is. And now notice how the acid is going to donate a hydrogen ion to the base, and likewise the conjugate acid over here is going to donate the hydrogen ion to the conjugate base. Setting that up helps you to know what you're looking at and what you're how to go about solving this problem. Now, like it makes sense that given that we're told that methylamine is a base, a weak base, you're given a Kb for that weak base. Methylamine forms salts such as methylammonium nitrate, which is what you see here. Here's the salt. And then it says calculate the hydroxide ion concentration of a 0.225 molar solution of methylamine. So all you have really is methylamine ionizing in water, and so it's this reaction. And you're going to find out what the hydroxide ion concentration is. I'm going to ice it. If I'm asked to find amounts of an ion from a reaction, I am going to ice it. And so I'm going to set up my ice table, starting off with my reactants, rewriting it if I need to. Reacting with water in an equilibrium. With the conjugate acid of the weak base and hydroxide ion and the conjugate base. So the amounts that are given to me is the initial amount is 0.225 molar. It's in molarity, so I write the units there. Not too concerned about the water because it's a liquid. I do want to know how much I have that ionizes and hydrolyzes in water. So I'm going to, I don't know how much. It doesn't tell me my percent ionization, though it does give me the Kb constant, so I can figure out how much ionizes at equilibrium. So some of this reacts to form these two substances. In the end, at equilibrium, I have this amount, 0.225 minus x, and then xx. My Kb is written as far as the expression is concerned. So I'm going to start off writing the expression, never skipping that step. It's quite important. And so I'm going to write my ions. And then I'm going to write my substances, my weak weak base. And so my constant's given to me, my Kb, it's 5.25 times 10 to the negative fourth. And that will equal to x squared. So x times x is x squared, and then 0.225. Now I know this is a weak base, so I can assume this is 0. So I'm going to zero this out, okay? And as a result, I can then solve it with much ease. I can write it as this and solve it with much more ease, okay? And when I solve for x, I get x equaling 1.09 times 10 to the negative 2 molarity. And that x is in fact hydroxide ion concentration. So this is my answer. It's also the conjugate base's concentration as well, but it's the hydroxide ion concentration, which is what I'm trying to solve for. So I'm going to label it as my OH minus. Now I'm going to B. All right. So in B, it says calculate the pH of a solution made by adding, oh, I feel like I'm doing a buffer solution here because I'm adding methylammonium. This is methylamine I'm adding methylammonium nitrate, which is right here. It's stated that it's the conjugate acid that you're adding. You're not interested in the nitrate part because that nitrate is not going to, it's a spectator ion. It's the methylammonium that you're interested in. And then so it looks like you're adding this amount of moles to this weak base. So you're adding the conjugate acid to the weak base. Yes, yes, you're thinking buffer, hopefully. This is my conjugate acid. This part right here is my conjugate acid. This is my weak base. And so I'm thinking buffer just like you. Hopefully you're thinking through it. If I have the acid and its conjugate base, I'm going to put this in red so it doesn't blend with the part A. I'm thinking POH. Okay, so I'm thinking POH. Why? Because I'm doing PKB. Plus log. And I'm going to do the acid, which is CH3 NH4 NH3 plus. The concentration of that over the weak base, which is CH3 NH2. So I knew to use the POH equation. Why? Because this is a KB problem. Look, it's a base and it's conjugate acid. So I knew this was the POH using PKB. Okay. It's a quick, easy plug-in. Trust me. All I'm doing is finding the moles. I just need to substitute my values in. So I'm taking the negative log of my KB value, which is 5.25 times 10 to the negative fourth, plus log, and I can leave it in moles, which is really nice. The methylamine is 0.0100 moles given to me, and then the methylamine, so that was methylammonium. Methylamine is this amount, so I'm going to have to multiply these two to get my mole units. And when I multiply those two values, I get, and I'll pull my calculator out, and I multiply 0.120, which is in liters, times it by 0.225. I get 0.027 moles. And then I take my POH. So I find my POH, and it ends up being 2.85. Now, to find my pH is just to take my 14 minus that 2.85, and I end up with, taking that difference, I get 11.15. Okay, so I don't want that dot there. Okay, so that is the answer to your A and B. Now, I'm going to need to figure out what C is asking. It says how many moles of either NaOH or HCl, so strong base or strong acid, state clearly which you choose should be added to the solution in B to produce a solution that has a pH of 11. Now, solution B's pH is 11.15. Now, which would you add to try to get the pH down towards 11? So from 11.15 to 11. You're right to say the acid because it's getting more acidic if you want to get the pH to be 11. So you're going to first add the acid, but it's asking how many moles of acid you would add. So you're trying to get the pH to be 11 in the end. So you're kind of working backwards with this problem. So what that would mean is you want the pOH to be 3 in essence. So you're going 3 and you're kind of working yourself backwards until you figure out how much base or acid you would add to get to that 11, or sorry, a pOH of 3.00. Okay, So I'm going to pause the video for a second and erase everything. I know my base in this case, which is methylamine, my weak base, is going to react with the strong acid. So I'm going to write a reaction for part C to show this calculation. And it's going to react with my, so here's my weak base reacting with my strong acid. I know it's an acid that I'm adding to my solution because the pH went down upon adding that acid, or an acid. And so this is a neutralization reaction. You're forming your conjugate acid of the weak base, which is methylammonium. Icing it, ICE. I'm going to see where I don't know something, I'm just going to call it X. So in the end, my hydrogen ion concentration, or moles of it, is going to be my X value. So I start off just like as I did in the B, where I have 0.0100 moles of methylammonium, which is right here. So I'll write that in, 0.0100 moles. And then I know methylamine is just multiplying these two values, converting this to liters first so I can get moles. I want to be consistent with the units I'm looking at. And so in multiplying those two values, I do get 0.027 moles. Now I don't know how much I'm going to add of this substance right here, of the acid. So then, and that's what I'm trying to solve for, is how many moles of acid I'm going to add to produce a pH that you see here of 11.00. So I'm going to lose some of this acid, make some of this conjugate base from that, and so I'm left with that many moles of my weak base. And then this is zeroed out because this is my limiting reactant, and I have this many moles of my conjugate acid. And once again, I see a buffer solution present. It's still buffering. That's why the pH didn't go down that much. Okay, the pH was 11.15 in part B, and then it went down to 11, which means there is a buffer solution present for that, for you to be able to add a strong acid, and there's still some weak base and its conjugate acid present. Weak base, conjugate acid. So I'm going to use the Henderson-Hasselbalch equation, and the equation is going to be POH equals PKB. I'm still doing PKB, log of the conjugate acid over the weak base. POH, if pH is 11, I know POH is going to be 3, so I can plug that in. PKB is given to us, so I take the negative log of 5.25 times 10 to the negative fourth. Okay, and then I'm going to add the log of this ratio that I see, which is my conjugate acid, methylammonium, over my weak base, methylamine. And what I'm going to solve for is this ratio. Okay, and when I solve for this ratio, I get this ratio to be equal to, out of room, I'm going to abbreviate this as HB plus over B, okay? And this ratio ends up being 0.525. Now, how am I going to solve this problem? Well, I'm going to plug everything in, meaning I'm plugging my methyl or my conjugate acid and my weak base into this ratio right here. And I'm going to solve it. Solve for x. That's my goal, is to try to find x because that's the moles of hydrogen ion. Once again, I'm a little tight on room, so I'm going to rewrite this, and perhaps I'm going to erase a little bit of this so you can see. But I'll rewrite it and substitute, well, I'm going to write it in black and write it very small, okay? So I end up with 0.525 equals, and I know my conjugate acid is going to be 0.100. Oh, making mistakes as I'm trying to squeeze in here, plus x, and then my weak base is going to be 0.027 minus x. So this is an algebra problem. I can solve for x in this equation, and when I do my math very carefully, working my way to solve for x, I do get x to be a value of 2.74 times 10 to the negative third. So that is my answer in the end for my acid. Okay, so please make sure you work through the solving of this algebraic problem. You need to make sure you can see x being what it should be in the end. The units for this x is moles, and it is moles of HCl that's added. Let's look at the last D. It says that if you take a volume of 100 milliliters of distilled water and you add it to solution C, which by the way is a buffer solution, what will it do to the pH? And this seems like a redundant question, but notice the pH will not change at all, or the pOH, because this is a ratio. And this ratio, as long as it's one of each of these, the acid and the conjugate acid and the weak base, you're going to see this ratio not to change at all, because with that dilution. Okay, so it has no effect on the pH. All right, from here on out, you're going to finish up the buffer solution the buffer worksheet, as well as anything else, all the FAQs following these problems. Okay. Work your way. The more practice you do, the more you can handle each of these unique types of problems, all with the same foundational concept. All the way through to 17. And here at this last end is a summary of all what to do during a titration, whether it's a weak acid strong base titration or a weak base strong acid titration. So it goes through what happens at different points that you'll be oftentimes asked, whether it's 0 of the acid, so it's just the 0 of the base. Sorry, this is a weak acid strong base, so no base added. So all it is the acid ionizing in water. And so you're looking at hydrolysis of the weak acid using the Ka. And then if you're starting to add more base and you're halfway to the equivalence point where you have a maximum buffer capacity, and that is when you deal with just the neutralization reaction, you'll notice that you have the acid and its conjugate base present. That's where you're going to use Henderson-Hasselbalch equation. And then at equivalence point, you really have to look at two ice tables. You're seeing that the moles of acid equals the moles of base when you're doing your neutralization reaction, but then after that you're going to see a lot of conjugate base, and we know the conjugate base of a weak acid is quite strong. It can stronger than water, that is, so it can hydrolyze in water, forming some hydroxide ions, and that will tell us the pH in the end for this solution. So you're dealing with hydrolysis, and of course the pH is going to be basic because of this hydrolysis of the conjugate base of a weak acid. Okay, it's a mouthful. Now we get to when you're past the equivalence point. At this point, you're still neutralizing the acid with the base, but there's going to be an excess amount of base, and that excess amount of base is going to determine the pOH, which helps you define the pH in the end. Now, when you are looking at a weak base strong acid titration, you run it through the same way. Now you have no strong acid added, sorry, and so all you have is the hydrolysis of a weak base. Okay, and so you're using Kb. As you add more acid, you're going to notice that there's a neutralization. Notice how the base accepts a hydrogen ion to form this conjugate acid right here. And when you're halfway through to equivalence point, you have maximum buffer capacity because you have the weak base and its conjugate acid in equal amounts. And that's when the PaOH equals the pKb, because this becomes zeroed out. Log of 1 is 0. Beyond that is just at the equivalence point, you have equal amounts of the base, the weak base, and and the strong acid. And at that point, you then see that the conjugate acid of a weak base is stronger than water, and so it hydrolyzes with water. So water breaks it up, and when water breaks it up, you're going to see the acid H plus and or the hydronium in this case because there's water present, and of course the base. So it gets broken up, the conjugate acid. And you'll notice that the pH ends up being more acidic because of this H plus ion that's formed in this when the conjugate acid hydrolyzes in water. There's so much hydrogen ions, or you'll produce hydrogen ions, which then produces this acidic solution at the equivalence point. Beyond that will be an excess of hydrogen ions because there's more strong acid, than the weak base. And so the excess acid is what's going to determine the pH of the solution. So this summarizes everything in your two different scenarios of titrations, a weak acid with strong base titration versus a weak base and strong acid titration. All right, example 22 was a base ionizing in water. Now we're going to deal with an acid ionizing in water, and that's what you're seeing, a weak acid. And I like to label my acids and bases so I can see. So here's my weak acid, and this is my conjugate base of my weak acid. Of course, I also see the conjugate acid too, which is right here. But it's hard to, unless you have water, to see who your base is. It's hard to see that that's your conjugate acid, the hydrogen ion being your conjugate acid, okay? But ultimately, I have the pieces of knowing where my acid and where my base is, so that I can work through these problems, these acid-base equilibrium problems. So it says hypochlorous acid, HOCl, is a weak acid commonly used as a bleaching agent. The acid dissociation constant Ka for the reaction represented above is the following. Calculate the pH of a 0.1 molar solution of acid, the hypochlorous acid. So it looks like I'm dealing with just really the acid ionizing as you see above there. So in A, I'm going to start off with HOCl, and it's ionizing in water. And I can put water in that reaction, but it really makes it harder. And I'm going to reorient my substances here. So I'm going to ice this. I want to know what the pH is at equilibrium. So ultimately, I want to know this at equilibrium, and that's why I'm icing this problem. I start off with 0.14 molar and no products at the start initially. I lose some of this acid, so a certain amount ionizes, making these two, the conjugate base as well as the conjugate acid. And then at equilibrium, it's just a matter of summing those two rows up, and here's my equilibrium. Now my Ka, since this reaction yields hydrogen ion, I know this is a Ka reaction. So my Ka for this reaction is expressed as products over reactants. Notice I'm still writing the expression. You get pretty good at this eventually. Hopefully you're still practicing writing the expression. And then my Ka is given to me as 3.2 times 10 to the negative 8th. And I have x times x, which is x squared, and then 0.14 minus x, which is the acid, hypochlorous acid's concentration at equilibrium. I'm going to assume x is small, so I'm going to make an assumption. Assume x is so small compared to the number that is being subtracted, which is the original concentration of my acid. And when that's the case, I can zero this out and cross it out, and I just have to solve this problem. So x, when I solve this, x equaling, in the end mathematically, I calculated this already, and it equals 6.69 times 10 to the negative 5th. And I'm going to keep with my sig figs. My sig figs of my original concentration, the measurement is 2 sig figs, so my answer should be 6.7 times 10 to the negative 5th. Now that is the concentration of X is either these two concentrations, and really we want the hydrogen ion concentration, so this is truly the concentration of the hydrogen ions. And so I'm going to put and label the rest. Now we go to B. In B, we are asked to write the correctly balanced net ionic equation for the reaction that occurs when NaNO, or sodium hypochlorite, is dissolved in water. So this is a solid. And this solid, when it dissolves in water, and I'll put solid, is going to form two ions, Na plus and OCl minus. So sodium ion and hypochlorite ion. And of course, upon doing that, we know that sodium is from a strong base. So we know this is a neutral ion. But this one, it comes from a weak acid. So this is the conjugate base of a weak acid. So we know this is going to go through another reaction. And the secondary reaction is between water and that conjugate base. So OCl, aqueous, is going to react with water, liquid, and when it reacts with water, it's going to be an equilibrium reaction. And because this is a negative conjugate ion and its conjugate base, it's going to accept a hydrogen from the water. So a hydrogen ion is going to move from the water to the conjugate base. And when that happens, I have yielding HOCl, which is hypochlorous acid, plus hydroxide ion. Now, if I want to write the overall net of this reaction, I know I'm probably going to deal with adding these two reactions out. And when I do that, I will get these two canceling out, and that's really all that I have left canceled out. So it's Na sodium hypochlorite plus water, liquid, forming sodium ion. And we can't cancel out sodium ion because sodium hypochlorite is a solid. It was originally a solid. If it was a solution, yes, you can probably count that as a spectator ion and cancel that out. Continuing on, hypochlorous acid plus hydroxide ion. So this is your overall net ionic equation for what's happening. And again, it comes with this idea that the salt is not neutral. This part is neutral, but this part right here, the conjugate base of a weak acid, is pretty strong, and it's going to hydrolyze in water, as you see here, to form your acid again and hydroxide ion. All right, let's move on to letter C. In letter C, It says, calculate the pH of a solution by combining 40 milliliters of the weak acid, 0.14 molar of the weak acid, and, oh, it looks like we're titrating it with a strong base. So we're going to see the reaction that occurs between these two. Here's your acid, weak acid. Here's your strong base. And I am actually going to get rid of my spectator ions, and that would be sodium. So my reaction that I'm going to write is going to be a reaction between my weak acid and my hydroxide ion, which is the part that will accept a hydrogen ion, which is the base. So here's my acid, weak acid. Here's my strong base. Sodium ion is a spectator ion, so I'm going to eliminate that out of the picture so I can concentrate on the species that are reacting. And I know that since this is my acid, this is my base, I know that a proton is going to be donated over from my acid to my base, leaving me with the following products. I'm going to have water forming. The hydroxide ion is going to become combined with the hydrogen ion to become water, and of course my conjugate base. Now with that, I want to react my acid and my base. I have to figure out how much I have of each, and I'm going to keep my amounts in millimoles when I do my math. So I'm going to take these two and multiply them, and that will give me millimoles. And then I'm also going to take my 10 milliliters and multiply by the concentration of the sodium hydroxide, and that will give me millimoles. And that allows me to ice my table, set up my ice table. So the millimoles I have for the weak acid is 5.6 millimoles. The millimoles that I have of the sodium hydroxide is 5.6 millimoles as well. I don't have, actually I don't even care about what I have of the water because it's not going to impact my equilibrium or my reaction, my neutralization reaction. So, but I do not have any of my products. So the reaction is going to be such that both the acid and the base are equal amounts, so I'm thinking we're at an equivalence point. And with that, we see that the acid amount is equal to the base amount. Thus, at the end of this reaction, you won't have any left acid or base, but you're going to have a lot of the conjugate base of the weak acid. And because of that, you know that this reaction is going to go through another side reaction. So much the conjugate base of a weak acid is going to hydrolyze in water, as you see here, in an equilibrium where it accepts a hydrogen, making HOCl. So this is HOCl from the water. So it accepts the conjugate base is going to accept a hydrogen to the water, from the water, and then leaving us with hydroxide ion. And once again, I'm going to trail where the hydrogen, the proton, is going to move. So it looks like it's going to move from the water to the conjugate base. And the base is always the proton acceptor. Now I'm going to ice this. And when I ice this, I need this conjugate base right here in molarity. And to get it into molarity is to figure out what the total volume is between the two when you combine those two together. And so there's 40 milliliters from the acid and then 10 milliliters from the base. So the total concentration is, or volume is 50 milliliters. And since I'm in millimoles already, since I'm already in millimoles, millimoles divided by milliliters will give you molarity. Now, why did I convert it into molarity? I did that because I am using this second equation right here, which I need my Kb expression to do, and KB expression is in molarity units. So that's why I knew I needed to get into molarity units back again. And this molarity value is 0.112 molarity. So I'm going to plug that into my ice table. I don't care what happens with water because it's a pure liquid. I don't have initially anything of my reactants and or products. I lose some of this of my some of my conjugate base ionizes, forming X amount of each of my products. And so at equilibrium, this is the amount I have of my conjugate base, and then X and X would be how much I have of the products. Now this is a KB problem. How do I know this is a KB problem? Because if, look, I'm producing my base when you're ionizing in water. So you're ionizing your conjugate base in water, producing a base. So this is a KB. Now you're still doing products over reactants. Do not include water because water is a pure liquid. So products over reactants, that would be your KB value. Oh, I'm going to write the expression out. I don't have much room, so I'm going to write it in up here. So my KB for this reaction is HOCl times OH minus, so products over reactants. And the KB value is in fact calculated by taking KW or KW divided by KA. That's KB. And when I do that, I actually get KW is 1 times 10 to the negative 14th. KA is 3.2 times 10 to the negative 8th. That will give me my KB, and my KB ends up being 3.13 times 10 to the negative 7th. And then I just plug everything in. I plug my x's, so this is x squared divided by 0.112 minus x. Now, recall I did assume earlier, I'm going to do both my assumptions and validations for both of these after this problem specifically. So then I assume x is small, so I'm going to cross this out, and then I solve for x. X ends up being 1.87 times 10 to the negative 4th. And I know what my X represents. My X actually represents the hydroxide ion concentration. And this is what's going to allow me to find the pH. So I'm going to find what is called pOH. So pOH equals negative log of this 1.87 times 10 to the negative 4th. And when I get my pOH, I get 3.73. Take 14 minus that. That will give me my pH, which is 10.3. So let's validate now. I'm going to put my validation in blue so that we can do each validation correctly. I'm going to start off with this validation. So all I do is take whatever x equals, which is right here, and divide it by whatever the original concentration that I zeroed out from. So this is the original concentration. So when x is small, so you take 6.7 times 10 to the negative 5th, you divide it by 0.14 and times it by 100. That's how you figure out your percent ionization for each of these problems. You take the amount that ionized divided by your total original concentration and times it by 100. When I validate the first validation, I end up with a percent that's quite low. As long as it's less than 5%, we're good. And this is less than 5%, which means we're good. Okay? for that first assumption. So let's now look at the second assumption. The second assumption is here's my original concentration. Here's what I subtracted it from. This is my original concentration of my acid. Here's my final concentration that ionized. So I'm going to take this, divide it by this, and times it by 100. When I do that, I take 1.87 times 10 to the negative fourth, and I divide it by my original concentration, which is 0.112, times it by 100. My validation results ends up being, so my answer is 0.167%, which both of these are less than 5%, and that means they're valid assumptions as far as the approximation method is concerned. Now let's go ahead and jump into D. So I'm going to erase everything onto D. It says in D, how many millimoles of solid sodium hydroxide would be added to 50 milliliters of a 0.5 or 0.20 molar hypochlorous acid to obtain a buffer solution that has a pH of 7.49. Assume that the addition of the solid sodium hydroxide results in negligible change in volume. So you're going backwards in this buffer solution, but let's set up an ice table and set up the reaction that is involved in this ice table. I know I'm reacting the base, which is the hydroxide part, to the acid, which is this whole weak acid right here. And so it looks like a titration, honestly, but regardless of whether it looks like a titration or not, you are still setting up an ice table to show for this reaction. So you're reacting these two substances. Once again, it's always good to identify who your acid is and who your base is. This is your acid. Here's your base. And we know the acid donates a hydrogen ion over to the base. And that's what I'm going to show, is the donation of a hydrogen ion to the base. And when that happens, you're forming water, and you're forming the conjugate base of the weak acid. So water is formed plus the conjugate base of the weak acid. Icing it, ICE. I'm going to work in millimoles because I'm feeling like the word buffer means Henderson-Hasselbalch equation. So I'm going to use the HH equation. I'm going to start off with millimoles. So what is 50? Multiplying these two values, what's this equal to in the end? It looks like it's 10. So 10 millimoles of the hydrochloric acid or hypochlorous acid. And then I don't know how much I'm going to add of this to be able to make that buffer solution that has a pH of 7.49. But I do know that I don't have any of these, but I don't even care about water ultimately in the end, because water is already in the solution, so it's not going to contribute to the pH of the solution. It's only the species that are acidic or basic. Unless if there's only water, then you can say that water does contribute by its self-ionization. All right, I'm going to lose some of this because it's a buffer solution, so I'm assuming that your limiting reactant is going to be your strong base. And then I'm going to make some of the conjugate base of the weak acid. 10 minus X, and then this is zeroed out because it's the limiting reactant, and X. Now I'm going to calculate because I have a buffer solution still, even after adding a certain amount of the base, you have a buffer solution because we have the weak acid and its conjugate base present. So you know that there's something to buffer the base, something to buffer the acid with the conjugate base right here. So there's always something. These two species are important for buffering both the acidic end or the basic end of anything added to this solution. So I'm using the Henderson-Hasselbalch equation, which is pH equals pKa plus log of the base, conjugate base, over the acid, weak acid. So I'm going to plug everything in. I've got my pH, which is 7.49. I know my pKa is, or my Ka is 3.2 times 10 to the negative eighth. And then I can just log whatever is in there, which is my conjugate base is X, and then 10.10 moles, millimoles, minus X. So this is all in millimoles, by the way, and that's why I like labeling, knowing what is my unit that I ultimately will end up for X. So this is some math, algebra, making sure you are sticking with your mathematics well. So when I take the negative log and subtract it and bring it over here, or add it, whatever ends up being value-wise, you end up trying to bring it over to here. When I do that, I end up with 0.989 equaling x over 10 minus x. And then I like to cross multiply and do math as I normally do math, which is algebra. And then I multiply this, I get 9.89 minus 0.989 times x. So bringing the x's over, I get 1.989x equals 9.89. And then solving for x, x ends up being equal to 4.97 millimoles of sodium hydroxide, but if you want to sig fig it correctly, it's 5.0 millimoles of NaOH that you would add into the solution to make that buffer solution of pH 7.449. All right, let's go to letter E. In letter E, it states, household bleach is made by dissolving chlorine in water as represented below. So you're taking chlorine gas, dissolve it in water to make this bleach here, hypochlorous acid. Now, it says calculate the pH of a solution if the concentration of the bleach in the solution is 0.065 molar. So let's look at 0.6. Here's your this is the concentration of this bleach. Now, pH is H, so here's the H here. What's the ratio between the two? Well, it's 1 to 1, as you can see. So this concentration is really the concentration of the acid, the H plus ions that you would be making from this reaction. And with that, it's as simple as just taking the negative log of that concentration. So in E, letter E, I just take pH equals negative log of that value, which is 0.065 molar. And when I do that, I get an answer of 1.2 pH. And so the solution is quite acidic when you dissolve chlorine gas in water. You're led to not only a weak acid, but really a strong acid out of this solution, hydrochloric acid. Okay, you're working your way through FRQ 18 all the way to 19, 20, checking your answers in between, 21, FRQ 22, and then the last one, FRQ 23. So make sure you work and practice these problems. The more practice you get, the better you will get at it.